Alright, so good day there. So today we will now jump to our next video tutorial on linear regression explained. So last time we discussed about how to run a simple ANOVA, a one-way ANOVA, and two-way ANOVA, and how to run post-hoc tests, and how to check assumptions, whether it is your data is normally distributed or it is homogenized. It's a subject on homogeneity. So I just want to feature my YouTube channel. I just um created it recently, and mostly the idea of this channel is to share with you about research, how to conduct research, how to run data analysis, and also scholarship, fellowship, my experiences across 28 countries and travel experiences, and also academic success, and also personal. So alongside it, also the professional English tutor, I'm teaching civil foundation English, and although my background is in forestry, so most of it is are related to uh, data analysis and finding the right scholarship. Maybe one of these videos will be able to help you out in terms of your dreams, ambitions to study abroad, how to apply for scholarship, fellowship, and studying abroad, and how to write a strong motivation letter, and how to be successful studying abroad. Of course, I'll also be sharing about how to write our competitive research proposal for scholarship and fellowship. My experiences as an international citizen traveling to countries and backpacking across 50 countries, that travel tips safely and planning. All right, so without further ado, let's try to now navigate to linear regression. So I think you are familiar with linear regressions. We all know that we do regression to be able to predict one variable to another. So in that case, for regression, we need two variables that are mostly numeric. So to be able to navigate here, so I'll make a new R script here, and this is my work environment, and this is where you see your craft or figures. So let me just do this way so that we able to really follow what's going on with the coding. All right, so let's now try to linear regression. So I'm gonna load the library. So again, I think you know how to load the library. So just load enter or just here click run, and it should work already. First is, of course, I don't have a data set, so let's just try to create the data set. And I want to write a data set with this one. So hit data. So I'll explain it one by one here. So first is forget about that. So this is the data. So this is DBH. So DBH. So DBH is so diameter or breast height. And here is we wanted to create an observations 50, mean 30, and the 6. So expect that this DBH is 1 centimeter. So expect that 50 observations, 30 centimeter, and standard deviation, which is 6. So I would say that our data would be not really uh different from each other because of the standard deviation, which is a bit lower. So for the height, we have 10.8 dividge, and just this is how we create our data set. So, okay, let's just make it simple. I'm gonna just use the dividge code and height, and let's do that. Now we could have created 50 observations for DVH and height. And now let's merge this data. So we have the table, DVH, and height. Now our data is already here. So we have the DVH and height. So again, when you do regression, you make sure that your variables or your parameters are numeric. So you'll not be able to run a regression when it is not numerical. All right. So I hope you understand. I understood that. So also based on my previous tutorial that we need to the scatter plot. So your scatter plot is really numeric. All right. So let's have a short. overview of our data. So you can see it's our data, like dimension data, and you have there, you can look at the expected observations to variables. You can also do the summary, just to look at summary. So see, because we have only two variables, so the summary is dbh and height. And the minimum is 10 for dbh, maximum is 42, mean is 30. So which is we already resetted this. You can see the mean is 30, and this we kind of already expect what kind of data we are doing here, because we basically just created a data set by uh, I use AI to create a data set. So for height, the minimum is 18 meters and the maximum is 46 meters, which is like, oh, that's a really high height. Imagine a tree which is 46 meters, but it's kind of unrealistic though. But this is for the sake of this tutorial. I think we can stick on that. All right. So now, since we have already the data, so let's just, run a simple relationship. So again, I have a tutorial about how to do the J point, box plot, scatter plot. So just try to look at it. And if you know more about details about it. And so for the visualized relationship, I would just say digiplot the data. So the data should be your in data here. And aesthetics, it is the dbh and height. So make sure that these values are numeric if you do the scatter. Gym point, the size tree, so let's make it 4, I would say 4. The size is just in the how does the size of your points, whether it's if you want to make it visible or not, then it's entirely up to you. You can also just change why. It really depends on your interest. So GM method, the method is linear modeling, true. And the title's relation between DBH and tree height and X, I want to label it as DBH. And the Y axis, so Y is in this side here, Y and X below, that's for DBH. So let's just run this. And there you go. That's it. I don't like the Jane point, which is really used. I want to change to 2. That's much better, I think. So let's see. All right. I think this is more great. So let's just try to enhance this. Zoom in was in our data. So that's really good. It's looks perfect to me. The relationship between DBH, so it's like the higher the DBH, the higher the height. Does that make sense to you? So again, because we set that height is on the y-axis and dBH on the x-axis. So this is the linear method. So you can see the data points in this block and the linear the line. So now as we will try to look at let's try to fit a simple linear regression model. So let's just bring it here, make it so visible. So again, when you do the linear modeling, is the simple way is this one. It's just this is one that's LM. So I want to say model. Not to write it again, just make sure that we know what I'm doing. So you write an arrow and here LM and height DBH, and this symbol here and DBH and data is equals to data. So make sure that data corresponds. So if this is what is written here, you have to put it here. So which data that you want to use, and make sure that your variable header, deviation height coincides. Height and deviation. And I just run that. And there you go. We already have the model here. It's already here. But we cannot see what's going on. So to see the results of your model, let's just say summary model. So make sure that here and here it's a line. You're actually summarizing the specific model. All right, so let's try to look at the model. So here the model is interesting. So what I want, this is a lot of information here. The minimum, and then I want you to look at the estimates. Look at the estimates and the DBH and here, and also the p-value, which is 3 asterisk, which means that it's highly significant. You can see here that there are significances DBH. So like DBH is highly significant to height. So now let's try to look at the how to interpret the. So this is how you interpret your coefficients. So for every 1 centimeter increase in dBH, tree height increases by 0.79. What does it mean? Where did you get these values? So if you try to look at the coefficients, and which is the estimate, so let's stick to the estimates. So it means this is just one increase in dBH, tree height increases by 0.79, so which is basically in this side, which the p-value is less than 0.01 is 0.00, which is highly significant in this size, in this case. And I will explain 68% variation on the height, which is the R R value is 0.68. So where did you get this 0.68? So let's just try to imagine where is this 0.68 R value. So here it's a 0.68, but the R adjusted R squared usually is 72. So I think you cannot just use this 70. It should be 72 in this case. So now let's try to look at plot. How to use plot. So plot is just model plot, which one, and see, you can see this is just how you check your model. So this is the fitted, the residual versus fitted. And another way to look at is this normality. Just gonna bring it here. So model two, which two? So now is the residuals, the cookie plot, which I've shown also. So when you look at the line here, that looks perfect to me. The data points, it's close to the line. And Shapiro is to look at the normality of the residuals. Residual is 0.06, so which is good. So remember what with my previous tutorial that when p-value is greater than 0.05, which is what we have here is 0.06. So our residual is good. So now let's like to look at the diagnostics table. So let's just bring this in our working script. So I'm gonna load this library room. But if you don't have it here, you just go to packages and install and just type in there like library, and then there you librarian. So no, sorry, this it should be room. Yeah. Now you just click this and then install, but I'm not gonna do that because it's already installed in my case. So let's try to look at tidy model. So you see there, it's just trying to look at, like tidy, which we want to clean the models. Intercept is this. It's basically what we had with our results here. We just try to look at the summary of our model. So there's a lot of information that is showing that what we really need is just the R squared value, the estimate value, and E value, and so on and so on. But in this case, for the high day, it's just trying to show you the most important part of the model. So just run this tidy model, and you can see the estimation and the p-value. That's 0.88, so like 0.0005, which is say it's highly significant. Another one is glance, just to look at, like a short glance of our model. So let's just run this, and okay, so why it's not working? Okay, so probably doesn't this one, but just to do it one more time. Okay, this one is R squared 0.72. This is our R squared and R squared and EIC. So what's an EIC? So EIC is a key information criterion. So basically, if you have a lot of models, let's say you have 5 models, and then you gotta use just EIC. So again, the lower the EIC, the best is the model. So with that, I think I'll try to uh I will try to have a video on how to use EIC and selecting the best model. So, but then this is just how you kind of, look at the model in terms of parameters that you are interested in. So basically, we are interested in R square and also the ESC value and the P value and so on and so on. So for now, let's just try to uh table 20. So model need, I think we don't need to run this one to predict values because really what we should is only a simple regression modeling. So now, how do you report that? So basically, you just report a significant positive relationship was found between deviation tree height, which is very visible when you do that. If you remember our uh, simple line in this case, so this is exactly as you just bring this in. Okay, you see, that's what uh, it refers to. This significant, and positive. So positive relationship and significant with the p-value with this. So this is how this is very simple way of interpreting your results. So the model explains 60%, so I would say 70% in this case. 70% here is 72 because based on this the based on our glance code. So always check your here R squared 72. So and then again for simple interpretation for every 1 centimeter increase in dB is tree height increased by 0.9 centimeters, which is like I don't know like how it's a strange data because imagine in one increase of dBH centimeter it also increased by 0.729 meters, which is 1 meter is that's a kind of weird data actually, but anyway, because we just created a data set, so it's what we are trying to show here is how to use the code and how to run a simple linear regression and how to interpret the results. And again, here residuals were approximately normally distributed. This is what we know. If the p-value is greater than 0.05, it means that your data is normally distributed. You can also look at this by running a simple like this. Remember the simple code. So data and then DBH. Okay, so if you try to look at this here, so it looks normally distributed to me. And all right, so it's because I want to data variables, DBH height. So let's just try to hide them just to make sure if the result is same. So let's just put height. All right, so same looks good on me. That's why Shapiro this point is higher than 0.05, and it makes sense. So I think that's all for this linear regression. And then basically you can just, you can do like this, you can just export this here. Oh, I like this one, but here this is visible, so I'm just gonna, that's why I can drag it like this, just to make sure your height, and you can see the linear modeling, uh, DBH5, and just click save, and then there you have it. Just go to your folder, and there, right, your figure, and that's good at me. I will just copy that and put it here, and we are going to our writing the story of our publication, and then boom. So I really like this simple like modeling. It's simple, but again, you have to know your data, what kind of data you have, so you can just simply apply this modeling if if there's no sense of running a linear model. All right, so I think that's all for this tutorial. And now let's next video will be multiple linear regression. So actually it's the same with linear regression, but now we'll be using different or we'll be adding another variable, and that's why it's called multiple linear regression. So I think that's all. Again, I Dr. Rodrigo, and if you have questions, clarifications, you may contact me at my email address, rafi@gmail.com, and my work email, rafi.rodrigo@ipso.edu.ph. All right, so let's see you for next video tutorial and have a great day.